Ooh, that's the most exciting thing I've heard today. Yeah.
Yeah, we're pretty excited about it too. It's just a demo for now. Like none of the blocks are interesting at all yet, but like it's sort of a proof of concept.
So blocks, I guess, are just empty and don't actually include any transactions or anything?
They include something that you could call a transaction, but it's just for all intents and purposes empty. Yeah, but they're they have like random data.
Oh, cool. That's still awesome. It doesn't seem like it's that much more from a Casper perspective, you know, to add transactions in.
Yeah, exactly. Like it's it should be straightforward to move to like meaningful blocks from here, which is why we consider this a milestone. And we won't be able to move to Rolang terms in blocks for a while anyways, because we need some more support from the storage aspect of Rolang, so that when you're running your fork choice, if you jump to a different chain, you can revert back to the common ancestor and go forward again.
Oh yeah. So when you say storage layer, do you mean like the tuple space stuff?
Yeah, exactly.
How efficient is that stuff?
We're not super worried about efficiency at the moment. So right now it's nothing impressive. It's like linear in the number of channels used or something like that. And also right now there's no easy way to roll back to a previous version of the tuple space. But what we're aiming to do is have like a Patricia Try style setup where you can go back to a previous state just by looking at an earlier node in the tree type of thing.
Cool. Seems reasonable.
But yeah, so from my end, update is distributed Casper is working. And
wait, real quick, do we want to start? Do we want to start the stand-up now? I'm happy to start. I was wondering if that's what we were doing.
Well, I see the little recording light here, so I assume that means we've started.
Cool. Yay.
Yeah. So if you want to go next, Nate.
Yeah. So finally got that massive, like, extremely big PR merged in terms of like refactor of the entire code base. So essentially it's like, we now specify the execution of the protocol up front and then kind of just like pass it to the simulator and say, run this thing, make messages like this and send messages here, et cetera, et cetera, et cetera. Which just makes like, it's well suited for the simulator, not particularly well suited for like, something in the wild, but it's good for, testing our hypotheses, et cetera, which is cool. Other than that, I've spent some time working on the abstract protocols state stuff that Vlad, I believe, mentioned last week. I don't know, I missed last week, but I'm assuming he mentioned it. But pretty much it's like thinking about all this kind of work we did, thinking about liveness and bivalence and stuck freeness, et cetera, et cetera. We're kind of exploring the abstract protocol space as much as we can. So just done some thinking in terms of that, trying to classify different like groups of states. It's a bit in depth, and I'm not totally like all the way through the line of thinking, and haven't had time to like catch up with Vlad about it. So probably we'll present that in full next week, whatever comes out of it at least. So yeah, that's it for me.
Sweet. Yeah, that sounds awesome. Looking forward to that presentation.
Cool. Gent.
Hey, I've been working with Michael Birch on the release. I guess there's nothing much from my end. Yeah, more than that.
Nice. Well, it's possible we just did the world's fastest Casper Standup. Anything else? Anyone have any notes, comments, questions for the group, etc.?
Oh, Nate, did you by any chance already figure out the sort of, I want to call like the sharding probability problem? Let me read it out. Um, so so it goes something like, if you have a huge bag of R red balls and like B blue balls, and if you pick one out of Y of the total number of the balls out at random, like what is the probability and variance of the ratio of red to blue balls being more than Z? Does that kind of make sense?
Yeah, kind of. I guess I'm very confused as to the relationship between that and sharding, but
Well, so this is basically picking the balls sort of represent the validators, and um when you pick one out of Y of the total number of balls, it represents splitting your entire pool of validators randomly into Y shards.
sure. Oh, that's interesting. Yeah, no, I've never heard of this before. When was this like brought up / suggested? I mean, I know people have done thinking about random sampling like this, but I've never thought about it at all. When did this come up?
Oh, so we had a meeting, I forgot when, maybe like Thursday or Friday last week. And basically, Kyle wanted some proof about like whether randomizing validators is actually worth the effort. And I guess he wanted to see some probabilities, or like especially the variance related to like how far we can shard without having to actually sort of have watchers that look at each reduction.
That's interesting. So, I mean, I guess this requires kind of like more complex assumptions about like percent of honest stakers and stuff, right? You know, like you kind of can say like, we can talk about like the number of honest validators on any given shard, if that makes sense. But to do that, I think it requires us to make I guess we cannot define it up front, but that's an interesting problem. I have not thought about it, no, but I guess if the question is randomizing even worth the effort, then like the simple example to say yes is just oh cool, hey Greg. The simple example to say yes is just to like assume that we're not randomizing and then like figure out what the cost of attack is and realize that it's essentially zero if you can pick where you're going, right? And it doesn't cost you anything to do so. It's like pick where you're going, get all your guys there, overwhelm the shard, and then attack immediately, right? So.
Oh yeah. I mean,
if that's what the question was, but
yeah, I think we noticed sort of like, I guess that point, but yeah, I guess how far we can sort of shard out is the question.
Yeah, it's a great question. I know that like I know Vitalik's done some thinking about this in terms of like safe sizes of validator pools and stuff, but and I'll see if I can dig anything up. But I personally haven't done any thinking about it now. But I'll see if I can dig something up and I'll shoot you a message.
Cool, that would be great.
Cool. How's it going, Greg?
Hey, how's it going?
Good.
Cool. Sorry I was a little late. I'm running a course, Introduction to the Design of Computational Calculi.
Where's the course? I want to take
it. Okay. So it happens the hour before this one. We had the unofficial beginning today. It officially begins on the 28th of May. In order to participate, I need a letter, and the subject of that email is Introduction to the Design of Computational Calculi, and in it I need answer to three questions. Who are you? Why do you wish to attend? And what is your aim?
Sounds wonderful. Okay, yeah, I'm gonna send you a letter.
Okay, awesome.
Thanks.
Sure, absolutely. Yeah, we had a great little kickoff meeting. It was nice. So who's gone so far? Can you give me just a quick rundown?
So quick recap is node release this week.
Yay.
Includes a Casper demo, distributed Casper demo, so that's pretty cool.
Woo.
And Nate told us that he's been working on the abstract state exploration of Casper, like thinking about how some states are lost when you include a message and that kind of thing. And next week he'll give us a more in-depth presentation on that work.
That's good. Yeah, I really was. I was very appreciative of Vlad's work on sort of characterizing states, and what goes into a state. I think the closer we can get to an algebra of states, sort of an axiomatic specification of states, over which you can have the safety proof. I think the better shape we'll be in, and that will then begin to align with two efforts that I've been working on. One is the using program state as protocol states, and that really picks out the process calculi. Then become they really come to the fore. It's hard to write down a distributed protocol state in the land of calculus because there's no distribution. Just as an example, right? So basically, the only choice you've got for a compositional or an algebra of program states that matches the axiomatic characterization of states would then be the process some flavor of process calculus. So that is a fairly clear thing. But also, if we have an algebra of states, it should line up with the axiomatic quantum mechanics, because there we have also a nice algebra of states that's related to a computational model. So in particular, we get some flavor of Hilbert space as your algebra of states, right? And then you get all of quantum mechanics to do your computation. So that lines up with this whole idea of quantum consensus that I'm exploring. Cool. By the way, though, that's huge progress. I saw Kent give the demo on Friday, and it's just so gratifying. This is awesome, guys.
Congrats, guys.
So Nate, can you say a little bit more about your exploration of states?
Yeah, sure. So pretty much the question that I've recently been asking is how can we characterize safety on common futures? So pretty much we're essentially trying to think about what is a maximally deciding consensus protocol. At least that's what Vlad likes to call it. And I might not do it justice here, but pretty much the idea is for any given protocol state, there are three types of states. There's states that we're safe on not having a common future with. So we've lost having a common future with this other state. We're safe, right. or we could be safe on having a common future with this state. So, for example, everything in our past we're safe on having a common future with. As of right now, it's ourselves. But and then the last relationship we could have with other states is bivalent on having a common future. And so essentially, I've been trying to figure out what states were bivalent on having a common future with. And the result is actually kind of surprising. I initially thought it was future states that included messages from non-Byzantine validators. So essentially the idea is that if you get messages from Byzantine validators, they don't matter. And so you can still be safe on futures that have, more messages in them, as long as those messages are from people who've already equivocated, because the people who equivocate essentially don't matter. They don't increase the number of faults, obviously, because they're already faulty. But it turns out that there's actually, it seems like, and I haven't totally convinced myself of this yet, but it seems like there's actually another group of validators who don't matter. And it depends on their weights and also your fault tolerance threshold. And so essentially we can include messages from these people as well in our common future, in a future state, and still be safe on having a common future with that state. So essentially the idea is that we're trying to figure out what states are bivalent bivalent in terms of having a common future with, and those states are different than what Vlad and I initially suspected, which is interesting. So anyways, been exploring that for like the past day or so. But yeah, hopefully we'll be able to discuss with Vlad and like kind of formalize it a bit more before the next stand up.
That's very nice. That's very nice. It's so close to the kind of thing that you see in relativity, right? You can talk about time-like distances and space-like distances, right? So when you have a space-like distance, there's no way you can have causal ordering, right? And when you have time-like distances, and as a result, it's hard to have common futures. And this is the whole light cone idea, right? So your light cone is effectively your common future. And when you have time-like distances, you can have common futures. So this is a very, very closely related set of ideas. You should also, if you're interested, there are a bunch of techniques that were developed by Maurice Herlihy and Eric Goubot for these impossibility results. So they provide a technical framework in which you can reason about the bivalent states that uses the techniques of algebraic topology.
Cool. That's interesting. Vlad seems interested in like the topological approach, because I don't know if you've seen like the metric stuff that he's been working on.
Yeah.
Yeah. So yeah, it seems super related for sure.
So here and Eric Goubot, and what we want is and concurrency theory. So there are like what are they're mainly called no-go theorems, and it's just like this whole host of techniques for doing that. Let me see. Yeah, so here we go. So this is Goubot's sort of summary paper that I can give you. And you may be able to find, like, if you don't have access to the ACM digital library, then that's the author list and the title. So you can probably find it on Sightseer or something else like that.
Thanks.
Yeah, absolutely. And then here's the tutorial. Well, actually, if you just use this search, this will get you a bunch of a bunch of related materials. Yeah.
Great. Thanks.
Absolutely. Yeah. Cool. Was there anything else we wanted to chat about? Did we cover all the major updates?
Think so.
Awesome. I guess we can yield back the time.
Yay.
All right. Talk to you guys soon.
So guys, congrats on the release. Bye-bye.
Thanks, guys.